Okay, so 2.7, we're talking about, I guess, 4 different things, basically. The first thing is symmetry. So a function can be symmetric across the y-axis. That means that the mirror is here. So whatever happens here has to be identical over there. That would have to match over there, maybe like that, so that it looks identical from either side. Whoops. But the way I was doing those dots, saying this has to be the same as over here, is that f of x and f of negative x have to be the same. That's what it means to say, oh, whatever happens over here happens over there. This is negative the same value that that was. So that reflection means whatever is going on with this x, when you go over to the opposite x, that's got to land the same place. So f of x is equal to f of negative x. So they're the same. So if you plug in negative x, you'll get f of x back again. You can also have symmetry over the x-axis. So this is symmetry over the y-axis. Symmetry over the x-axis, unless it's just the constant function 0, is not a function. Because if I put a point here, then there has to be a mirror over here. So this is failing the vertical line test of being a function, which is to say this single x has 2 y's, so he had 2 arrows, so that's bad. So this makes it not a function unless it's just y equals 0. But this means that if you plug in negative y, you'll get the same thing as if you plugged in y. So it could be that x is a function of y, but y is not a function of x. And it would just basically be if a b is on the graph, then a negative b is also on the graph. Okay? You can also have origin symmetry. Origin symmetry, the origin is this point 0, 0. That point is not meant to be indicated as on the graph. So if you have a point up here, then its mirror is over here. So down there would be like that. So it goes across twice, basically, over. So if we had, say, down here, then it would have to be mirrored up there. So something like that could be origin symmetric. The other thing is to note is if it's a function, then if f is a function, oh, this also means that f of negative x is negative f of x. So ab is on the graph, then negative a, negative b also on the graph. Okay, so if f is a function and symmetric over the y-axis, then f is called even. If f is a function and f is symmetric over the origin, then f is called odd. Okay, so to think about why they're called even and odd, let's consider just polynomials. If you have, say, f of x equal to x squared versus f of x equal to x cubed, if one of these is going to be odd and the other one's going to be even, you'd want this to be odd and this to be even, because the only difference between them is the exponent, and in fact they are. So here's x squared. I'm not doing a very good job of drawing that. X squared symmetric over the y-axis, x cubed symmetric over the origin. Okay, to prove it algebraically, f of negative x is negative x squared is x squared again, f of negative x cubed, negative x cubed. Okay. So if it's an even function, then when you plug in negative x algebraically, you'll get f of x back again. Visually, it's symmetric over the y-axis. An odd function, if you plug in negative x algebraically, you'll get negative f of x. and visually it's symmetric about the origin. We also talk about in this section when f is increasing, decreasing, and constant. Increasing and decreasing and constant are all just like we read. It's all left to right. So if I have, say, this function, and I'll just pretend that's negative 1, 2, 3, 4. Probably needs another 1, 6. Okay, so it's increasing as long as from left to right it's going up. So it's increasing there. It's decreasing when it's going down from left to right. And then it's increasing here again. Whenever you're asked where something occurs, where is a maximum, where is a minimum, where is it increasing, location is always given by x's. Value is always given by y's. So we wouldn't say it's increasing on whatever these y values are. We'd say from negative infinity, it keeps increasing until right here. This is the location, negative 1, 2, 3, 4. Also, it's increasing from here, negative 1, on to infinity. It's decreasing just on this little bit from negative 4 to negative 1, and that's it. If it suddenly here went like that, then we would have said it's increasing from negative infinity to negative 4, and then negative 1 to 3, and we would have said it's constant from 3 on out to infinity, because constant just means a horizontal line. If we are increasing up to a point, like here, and then we start decreasing, then that means that this is a maximum, a local maximum. It means there's a little area around here where this is the biggest value, or at least nobody's bigger. Then I decrease to this point, and then increase again. So this one's a local min, local minimum, because as I put a little circle around that, nobody's smaller. Then up here, we have a local max again. All of these are a local max because there's nobody bigger nearby. So local min and local max is another thing we're looking at. The last thing we want to look at is a piecewise function. I'm going to make one up, and I'm going to color code it. Okay, so f of x equals, I did not give myself enough room. F of x equals, so you'll first be given a function, so maybe negative x, from for x less than negative 3, say. And then the next one, maybe, let me make this 2 actually, negative 2. The next one might be x squared, and it'll go from negative 2 inclusive up to, say, 1. And then let's say f of x is just 3 after that. Okay, so I'm going to put this graph. I have important points here at negative 2 and at 1. So I'm going to be sure and put those on there. Now I meant to color code each of those, so I'll just do it this way. Okay, I did that with my trackpad, that was a mistake. So this is going to be my pink one. So I'm going to go up to x equal negative 2, right here. This is where things change. This is not an asymptote, this is just a dotted line to indicate to me where to stop. I should have put at least a couple of things to the either side. Okay, so if I go to -2, and to the left of it, I'm on the function -x. So if I could come over here, that would be 0, 0, -1, +1, -2, +2. I can't plug any of those because they're not in the domain. So I'm going to put a circle because that's actually where the function ends. And then there's the -x function, which is theoretically still going through here. Okay, so there's -x, but I only highlight it there. Maybe I should have just made dots for all of it. I'll do that from now on. Okay, so blue. I want x squared, which goes through 0, 0, 1, 1, 2, 4. So I'm going to dot it. For the moment. And then, here's my blue. I'm going to fill it in only from -2 to 1. So I'm going to go to 1, and it's a filled in dot because I have the equal sign. Go to -2 up to that 4, fill it in. And then three, it's just this horizontal line, but I'm only starting there at 1. So I go up there and it's not got an equal sign, so it's an open circle, and then it just goes like that. Okay, so then if I were to ask, say, what is f of 0, you'd come over here and say, well, 0 is not less than -2. 0 is between -2 and 1, so I plug it in there. F of -5. -5 is less than -2, so I plug it in there. So -5. F of 12. 12 is not less than -2. It is not between -2 and 1. It is bigger than 1, so it's 3. Okay, so that's how to kind of graph it and how to look at it. This is called a discontinuity. It's also a gap, a jump, open circle, closed circle. A continuous function, I could have made this continuous by, instead of saying f of x equals 3, if I would have said f of x equals 1, then I would have gone straight across from there. And I would not have a discontinuity here because they line up. So if from either side where you see the 1, if plugging it in to both of them results in the same value, then it's continuous there. I think I'm going to make the problems a separate video for this one and post this as the introductory video because this is a lot of stuff going on. So I will start on that now.